Now you see here, so in this example you see module. Okay, so this always block and this always block, both the always blocks are waiting for the passage of clock. Okay, so passage of clock will come after 10 time unit. Okay, so at 10 time unit, this is non-blocking. Okay, so this right hand side will get evaluated. Okay, but during that time the value of q is 0 itself, because initially we mentioned q equal to 0. Okay, so non-block left right hand side of the non-blocking will evaluate, and at the same time $right will execute in the non-blocking assignment. So it will execute at active event q. So in that case you will get the value of q equal to 0, because non-blocking will update the value of the q at non-blocking assignment event. Okay, so after that, after executing this $right, you will get the value of q equal to 1. So that value you can't see in this display. Now how to overcome that thing with the help of programs block? You see, program block will execute in reactive region. So reactive region will come after non-blocking assignments. So all the output updations you can find, those will get reflected in the test bench. You see, so this program block will execute at reactive region. So at passage of clock, whatever may be the value of q, so during that time this value is getting updated. Okay, so you will get the value of q equal to 1. If we practically see these things, you see here how our simulator is working. So what do you have to do? You go to the source where your program is. So after that you open that file. So this is the code which we have seen before. Okay, so this is the code. So $right is there inside a module, and other $right is inside a program block. Okay, so we will see how our simulator will give the result. Okay, so first we need to compile the code. Okay, so vlog sv dff.b. Okay, after that we need to simulate our code. So now simulating. So after simulating, you run the values, you run the simulation. Okay, so you see, so in module, so this message is from module. So during that time you have not seen the updated values of the DUT, but in program block, whatever display is there, you will get the updated values. Okay, so here the value is getting updated, and after that you will find this display is executing. Okay, so you see how in this way we are able to avoid the race conditions. Okay, so these are the race conditions. Now coming to the next point, the bit type shall be used for all clocks and reset signal. So bit, we know that bit is two state type. Okay, either you will get a value of 0 or 1. Okay, so those are only the valid values in the real hardware. So why they are specially saying these things, that if the 4-state logic type such as logic is used to implement the clock signal, the initialization of those signal to 1 tick B0 may be considered as an active negative edge by some design component. So the alternative of leaving the clock signal to 1 tick BX while the clock edges are being delayed as per the previous rule may cause functional problem if these unknowns values are propagated. What they're trying to say is bit. Okay, so bit objective is suppose you are saying bit clock. So this clock has either 0 or 1. Okay, so if you are not mentioning what is the value of clock initially, so by default it will take 0. If you are defining logic clock, so what is the value of clock? 0, 1, x or z. If you are not explicitly defining, it will take x. Okay, so now when you are assigning clock equal to 0, so there is a transition from x to 0. Okay, so this will take that thing as a transition. But if you take example here, okay, so it is 0 only, so there is no transition. So in that case no event will trigger here, because it is not x to 0 transition, it is 0 only, so no event will trigger. So event will trigger when passage of clock will come. Okay, so here why event is triggering at 0 simulation time, because there is a change of signal from x to 0. So that is why your block is able to see the transitions. But in system Verilog, because we are having 2 state, so by default it is 0. So there is no transition from 0 to 0 is not a transition. 0 to 1 is transition. So in this way we can avoid some of the race conditions. The timing relationship of the unrelated clock signal should be randomized as a part of test case configuration. So what they're trying to say is like when you're configuring your clock, like you can say that clock, now suppose you want to verify your design at different frequencies, so you just go and change the parameter value of the clock where we are generating. Instead of generating hash 5 clock equal to not of clock, you generate hash 6 clock equal to not of clock. So if we are keeping that thing as a separate module, we can configure that with for different frequencies. Okay, but not only you have to mimic the time period, you have to mimic the jitters, all those things. So those are called offset. So you see how they are mimicking dollar random percentage 100. So dollar random may give you any value. Okay, so in that case you are mimicking the offset also. Okay, so you see percentage offset. So this is the offset, how you have to mimic the offset. Actually they made this thing very complex. Okay, we should make this thing very simple. So like this they are mimicking the this offset, clock offset. Okay, because we know that jitter may come at any time. Okay, so in that case we have to mimic jitter also in clock. So to enable test to control the random clock relationship values, these values should be randomized as a part of test case configuration descriptor. So we know that we can't predict jitter. Okay, so offset should always be random, so it may be any value. So that is what they are trying to say, how to model the signal layer in this test bench infrastructure.